This video presents a couple more convergence tests for infinite series. And the first one is called the comparison test. Let me write down what it says. Let AK and BK be series with positive terms. If I know that A sub k is less than or equal to B sub k, then B sub k convergent implies that A sub k is convergent, and A sub k divergent implies that B sub k is divergent. So the idea is this: to test if a series converges, we're going to take a known series that we know whether it converges or not. Say like 1 over k squared, for instance. If my series happens to be less than the 1 over k series, or less than or equal, then I know that my series is going to converge. However, say I have a series, and this time like AK is like 1 over k, and BK is greater than or equal to that, then I'll know that BK will diverge in a situation like that. So they kind of give us half the half of the whole answer, but not quite. So let's do some examples to illustrate this particular method. Here I'll start with sine squared of k over k squared. And this one's not going to be so bad because I'm going to compare it with 1 over k squared, and this is why. We know no matter what, sine of theta is less than or equal to 1, no matter what. That means that sine squared of theta is also less than or equal to 1. You square 1, you get 1 squared, it's still 1. So that means that up here on the top, when I look at sine squared of k over k squared, I know that that's less than or equal to 1 over k squared, because I know that the numerator is less than or equal to 1. Thus, I know that my series k equals 1 to infinity, sine squared of k over k squared is less than or equal to. And with positive, a sequence of increasing terms, that's good enough. This shows that this particular series is going to converge because I know that 1 over k squared converges. So the series converges. Let's go to the next one. Well, this one's not going to be so hard either because it's easy for me to see the following. I know that k times 10 to the k is always going to be greater than or equal to just plain old 10 to the k. Because k is starting as at least 1, so for every k this is going to be true. That means when I take the reciprocal, 1 over k times 10 to the k is going to be less than or equal to 1 over 10 to the k. But then we know that that's going to converge. Let's go ahead and throw this in. Here's a sequence of inequalities that we now have. I have 1 over k times 10 to the k is therefore going to be less than or equal to the sum from k equals 1 to infinity of just 1 over 10 to the k. And this here is a geometric series, so we know it converges. But if you want, you can go one step further. This is equal to 1 over 1 minus 1/10, minus 1 because it doesn't start at 0. And, well, whatever it is, that's less than infinity. So the series converges. By the comparison test. I'll just do comp test. Now, you might be thinking about why this may be true, and I think I've mentioned it before. I don't have to prove it anymore because I did it already. Was it in this situation here, all you have to do is prove that the series is bounded above, and then you're going to automatically have convergence. So there's a few examples for the comparison test. The next comparison test is called the limit comparison test. It's similar to the previous one, but just a little bit different. So let a sub k and b sub k be series with positive terms. All right, suppose these are two series of positive terms, and the limit as k goes to infinity, a sub k over b sub k equals some number L. We have three cases then. If L is between 0 and infinity, that means L is positive and finite, then both series converge, or both series diverge. If L happens to equal 0 and BK converges, then AK also converges. If L equals infinity and BK diverges, then AK also diverges. So I'm not really doing a complete proof. Let's call it a proof outline. I think your book uses that term, so I'll do the same thing. So if we have the limit as k goes to infinity of AK over BK equals L, L is just going to be a number for right now. Let's just say L is between 0 and infinity. Okay. Then for large k values, if you remember, most of our arguments will say something like k is greater than some mysterious number capital N. So let's say it suits that. Then if there are large values, we do know that A sub k over B sub k is approximately equal to L. Then A sub k is approximately equal to L times B sub k. And then we have the series A sub k. I don't know where it starts. Let's say it starts at 1, goes to infinity. It can start at whatever. You'll have A1 plus A2. And you'll just have A terms up until you get to the mysterious n. And then from that point on, each of these was approximately LBK. So I'll throw it in there. So this is now this should be an approximate symbol, not exact. And we still get the first capital N terms. But now I'm going to replace AK with LBK. Now, if it's true that B sub k is convergent, that means I'll be able to factor the L out front. And since BK is convergent, we know that this piece right here is finite. And no infinite series has infinite terms as far as a number is concerned. These are all going to be finite numbers. This is just the sum of the first capital N terms, which is some number. L, of course, is just some number, and its times just some number. So A sub k converges. What that means is that, and once again, I don't know where it started or anything like that. I put the 1 in there for some convenience. One other way of writing that it's convergent is to write that. This here is the same as A sub k converges. I do feel sort of necessary to explain the other two parts, though. I just, at least to get a feel for it. If the second part says if L equals 0, imagine if this is equal to 0 and BK converges. That means that AK was so minimal in its efforts that BK in its converging was still way more than A sub k, and it went to 0. So A sub k would be far less than B sub k. And then in the situation where L is infinity here, if L is infinity, AK is seriously outrunning B sub k. And if we know that B sub k diverges, it's already going to infinity. This has to go to much more infinity just to win this race and become infinity as a quotient. Now, the limit comparison test is great when you know the net exponent. I put that in quotes because the term is not found in your textbook. I just made it up, but I'll explain what it means in this next example. All right, here I've got the square root of k over k cubed plus 1. This is where I'm going to talk about net exponent, and I'll see if you can hang with me on this. I'm going to rewrite it as k over k to the third plus 1, and then I'm going to write it to the 1/2 power. So when I'm talking about the net exponent, find the highest exponent anywhere in the problem, and that's where you see the 3 here. But when you think, now the 1 is not important. In the scheme of things where k is a large number, k cubed has way more importance than the 1 does. Similarly, anything like this, k is actually changing and going to infinity. K cubed is going to infinity. The 1 is just sitting there doing nothing. However, if you're thinking of k cubed to the 1/2, that's k to the 3/2. Now on the other side, up on top, is a k to the 1/2. So what I'm thinking of as far as net exponent is I'm thinking of 3/2, but then I'm thinking of subtracting 1/2 because of the way exponents work when you divide by them. You take the power of one and you subtract the power of the other one. So in my mind, I'm thinking of k to the 3/2 minus k to the 1/2, or k to the 1. So let me write this all down. So I get k to the 3/2 minus 1/2 equals k to the 1. So I'm going to limit compare to the series from k equals 1 to infinity of 1 over k. That's 1 over k to the 1. Now watch what happens when I do it. It doesn't matter who you put on top or who you put on the bottom. It really doesn't. So we're going to do the limit as k goes to infinity. So I'll put the 1 over k in the numerator, 1 over k, and then down here I'll put this stuff. I'm actually going to break it up. Do I want to? Yeah, I'll break it up. So I'll have the square root of k divided by the square root of k cubed plus 1. Now, when you fix all these fractions, you're going to get the limit as k goes to infinity, 1 over k times k cubed plus 1 all over radical k. I'll go one step further. I'm going to multiply this together. I'll get the limit as k goes to infinity, k to the 3rd plus 1 divided by, this is k to the 1 times k to the 1/2. So that's k to the 3/2. Hopefully you see it's going to measure up. Then I'm going to go through and divide the numerator and denominator by 1 over k to the 3/2. Alternatively, if you want to use L'Hopital, you probably can. Actually, I wouldn't say that. I'm just rewriting it, actually, I think. Now, when k to the 3/2 comes inside of the square root, you've seen this enough, it becomes k to the 3rd. So when I have that, I'll have k cubed over k cubed will give me 1, and then I'll get 1 over k to the 1/3. To the 3/2. To 3, sorry. Just as a remind you, the square root function is continuous, so I can actually do this. And that equals 1 plus 0, which equals just 1. So we know now both series are going to converge or both series are going to diverge. Since this series is divergent, we know that both series are divergent. And our series converge or diverges by the lim comp test, the limit comparison test. If you can sort of feel the net exponent like I've been explaining, then it makes a lot of these problems very simple. And I'll show you in just a minute. K equals 1 to infinity. It's not good enough, though, to say that on a test. I'll explain. 1 over k radical k plus 2. In my mind, the k's dominate, as they always do, because they're the variable. This is k to the 1, and here is like k to the 1/2. I forget about the 2 for a moment. K to the 1 times k to the 1/2 is k to the 3/2. So my net, I'm going to compare this to, my net exponent in this case is 3/2. So I'm going to compare it to Whoever starts to start them at the same, it honestly doesn't matter if you start them at the same at all. Any of these could start at some number, and this could start at some other number. It really doesn't change any of the theory whatsoever. I'm going to change this over to 3/2. And now let's take a look at the limit. As k goes to infinity. For variety, I think I'll put this one on the top this time. And then just as before, I'll flip fractions. So I'll have k to the 3/2 divided by k square root of k plus 2. And if you want, right here, I can take out a k and change this to a 1/2 by canceling that. And then do the thing as I did before. Divide top and bottom by k to the 1/2. And you'll see that this turns out to be 1, just like all the other ones. So both series converge because this is a p series. It converges. This is a known convergent series, and therefore this converges. So 1 over k to the 3/2 converges because 3/2 is greater than 1. It's a p series. So our series converges by the lim comp test. This is an interesting series. What should I compare it to lim-wise? After I wrote this, I realized that there was a better comparison to do with it. And I'll tell you what that one is after I try to use the limit comparison test here. This to you may feel, I'm not sure what sine is going to go between negative and 1 for its whole existence. So this top is going to go from 1 to 3, no matter what. It's kind of fixed. It's at least bounded. Let's take this. So what remains is the thing that's moving around k. Like, that's doing some movement, but I don't think it really has a lot of effect on things. So I'm going to try 1 over k to compare with. So I'll compare. With, starts at 1, k equals 1 to infinity, 1 over k. Let's see what happens. So I'll put the 1 over k in the numerator, and then here I'll put 2 plus a sine of k slash k. And that equals the limit as k goes to infinity. So here then, when I flip the top and the bottom, I'm going to get 1 over k times k over 2 plus the sine of k. So the k's will cancel. And here I'll have 1 over 2 plus sine of k. Well, unfortunately, this limit does not exist. It does not end up being a number. So I can't, it's not infinity. It's not 0. It's not anything. It just does not exist. So this test, the test fails. Fortunately, it's very simple to fix it, though, and get the right answer. You can do this. You absolutely, positively, certainly know this. Sorry, that's the wrong way to go. I do know that it's greater than or equal to k equals 1 to infinity of 1 over k. Why do I know that? No matter what, sine is greater than or equal to -1. So 2 plus sine is greater than or equal to 1. The k I did not have to change. Unfortunately, this guy over here is infinite, so that forces our answer to be infinite. So it diverged by the comparison test. Now this is interesting. The 3 to the k grows much quicker than the 2 to the k. So since 3 to the k is sort of like a highest power, if you will, this 2 to the k is insignificant in comparison to the 3 to the k. So my point is I'm going to limit compare with the series k equals 1 to infinity 1 over 3 to the k, which you know that converges because it is a geometric series where the base is less than 1. So when I do the comparison, I'll have 1 over 3 to the k divided by 1 over 3 to the k minus 2 to the k, and that equals 3 to the k minus 2 to the k all over 3 to the k. And then I'm going to do something very simple. I'm going to rewrite this as, if you break the fractions up, you'll have 3 to the k over 3 to the k minus 2 to the k over 3 to the k. So I have 1 minus 2/3 to the k power. And you ought to know by now, when this base is less than 1, this part will be going to 0. So we'll end up with 1 minus 0 equals 1. And so both series converge. And our limit, our series, converges by the limit comparison test. An almost identical problem is like this: k equals 1 to infinity 5 over pi to the k plus e to the k minus 2. I'll leave it to you to figure out what to compare it with, but like I said before, the most powerful of all these terms is the pi to the k. So mimic what I did in the last example to show that this converges. This is an interesting one here. I'm going to do maybe, I don't know, I think I can use what I did before. You probably should know that tan inverse, as k goes to infinity, no matter what, tan inverse only outputs numbers between negative pi over 2 and pi over 2. So you'll have pi over 2 in the numerator over k squared. I'll pull the pi over 2 out front. And clearly, you could do that now that you know that the series converges. So this pi over 2. And look, that also works if the series is all positive terms, even if it doesn't converge. We're not going to be concerned with that, though. Anyways, this series here is known to converge. So I used a comparison test with a known convergent series. Any constant times 1 over k squared series is going to converge. So this is convergent by the comparison test. I think I'll end with less than infinity so you know what I'm talking about. I think with this series, the first thing I'm going to do is rewrite it as k equals 1 to infinity of 1 over k to the 1 over k. Now let's take a look at that exponent there. What is 1 over k? Well, I think 1 over k, as k gets bigger and bigger, this is certainly going to be less than or equal to 1. So then k to the 1 over k is going to be less than or equal to k to the 1. Since k is positive or anything like that, I don't have to worry about switching these. But now I will on the next step. So therefore 1 over k to the 1 over k is greater than or equal to 1 over k. Well then, our series is greater than or equal to the 1 over k series, and we already know that that equals infinity. That's the harmonic series. So our series diverges by the comparison test. Now this one is sort of interesting. What are you going to compare this with? Well, that 1 over k that's inside of there, this series does, I mean, the terms go to 0 because as k goes to infinity, 1 over k goes to 0. Sine of 0 is 0, so that part, at least it's not going to diverge that easily if it diverges or not. So what are we going to compare it with? Well, you ought to know, the way this is structured here, this is sine squared of something going to 0. So you should remember that sine of theta over theta equals 1 when the limit as theta goes to 0. This is one of the first limits they ever gave for this. Now watch what I'm going to do then. So if theta happens to be 1 over k, then I'm going to put a 1 over k down here too, right? So I can have a 1 over k here and a 1 over k here, but k will be going to infinity. You'll see in a minute. However, I have sine times sine. This is really something squared. So what I'm going to do is, what I have then is limit as k goes to infinity, sine of 1 over k divided by 1 over k equals 1, because this is approaching 0 and this is approaching 0. Now I have sine squared of 1 over k. So what if I compared that if I compared regular sine with 1 over k, why don't I compare sine squared with 1 over k squared? Well then, this is going to equal the limit as k goes to infinity. I'm going to write it more formally here so you can see it. That's 1 over k squared. Then I'm going to break this fraction up. And there I have it. This is exactly what I was talking about. This piece is going to 1 and this piece is going to 1. This equals 1 times 1, which is 1. So we actually compared our series with 1 over k squared. So since 1 over k squared converges, our series converges by the lim comp test.